Hello once again, this is the Pencrest High School AP Physics 1 video series. This is video 7F, Angular Momentum. Now we've already had an entire unit on linear impulse and momentum. Objects that are rotating also have momentum. We're familiar with the standard linear momentum, which we use for linear momentum, P equals mv. Knowing the analogies for mass and velocity, you should be able to predict the formula for angular momentum. The symbol for angular momentum is a capital L. L equals I times omega. I is the rotational analogy for mass. Omega is the rotational analogy for linear velocity. The units for angular momentum are kilogram meters squared per second. Again, the radians in the omega term, radians per second, go away because we want them to. And we have the units for rotational inertia, kilogram meters squared times radians per second. We're left with kilogram meters squared per second. Now, the classic example of a rotating object that has angular momentum is a figure skater who goes into a spin. So in figure A, the skater typically goes into the spin with her arms out, usually one leg extended away from the rotation axis. This tends to maximize the rotational inertia of the skater. So when she goes into the spin, she has some angular momentum I times omega, and what we see is that she brings her arms in towards the rotation axis, brings that other leg in towards the rotation axis, and because we are redistributing the mass closer to the rotation axis, this tends to decrease the rotational inertia of the skater. Now, because angular momentum is conserved, again in the absence of any external torque, angular momentum is conserved, so the angular momentum before equals the angular momentum after. Because I2 is less than I1, omega 2 is greater than omega 1, and the skater speeds up, and we see spinning very rapidly. Now, what we find is that the kinetic energy of the skater increases when she pulls her arms in because the kinetic energy is a function of omega squared. Even though the I decreases in 1/2 I omega squared, the omega is squared, and it increases by the same amount that the rotational inertia decreases, so kinetic energy tends to go up. Typically, the redistribution of the mass as she pulls her arms in, she's doing work on herself, and that by redistributing the mass, that work comes out as increased rotational kinetic energy. Okay, now we're also familiar with the linear impulse. We called it delta P, the change in the momentum. We have a couple of formulas for that, m times delta V and F times T. If you apply a force for some particular period of time, that will tend to change the linear momentum by an amount equal to m times delta V. The rotational version of that, delta L, is also I times delta omega. In order to change the angular momentum, we need to apply a torque for a particular period of time. And we find that net torque times time is also equal to delta L. This is the rotational analogy for linear impulse or linear momentum. We want to contrast this with the torque times displacement. which provides work done, rotational work done, and tends to increase the rotational kinetic energy. So on one hand we have torque times displacement, which is work done, and in this case we have torque times time, which is angular impulse. Okay, that's it for angular momentum. And next up is waves and oscillations. Until then, see you again soon.